all the hunters lay down their guns. Tell them that the tiger needs a little bit of love. Let them run the jungle, let them roam their land. Then stand back and marvel, what a beautiful cat. 'Cause I saw a tiger, now I understand. I saw a tiger, tiger saw me.
Hey y'all, Joe Exotic here, Tiger King. I'm here to teach you about exponential growth and exponential decay and compound financial problems. I'm going to teach you how to run a business. That's right. So grab your notes. Let's take a look at how these formulas rock and roll. Ridiculous. Ridiculously good. Ridiculously good looking. Okay, so I've got 3 problems I want to show you with these 3 formulas. So if you don't have this printed off, don't worry about it. Just grab a piece of paper so you can have the formulas written down already to reference. Okay, so this first one is going to be our exponential growth function. All right, we're going to model these word problems. And the formula that we're going to use for growth looks like this. Y equals A times 1 plus R to the T. All right, so A, that should be familiar from when we were graphing on Monday and Tuesday. A is that initial value. Initial value. All right, so it's what it starts at. Then in the parentheses is your base, but instead of using a B for base, we're using R for the rate, right? The rate at which it grows. And then T here is going to stand for time. All right, since it's a real world example now, we're going to use T for time instead of the X that we had earlier in the week. All right, so here we go. The original value of a painting is $9,000. So that's your initial value. So we have Y equals $9,000, parentheses. The value increases by 7% each year. So that's going to be our rate. Be careful when you plug it in here on your paper. You want to drop that percent symbol. And when you drop the percent symbol, that means you have to move the decimal 2 places over to your left. So 7%, that's the same thing as 0.07. So we have 9,000 for our initial. It's growing by 0.07, aka 7%. And we want to find the painting's value in 15 years. Okay, so the time is 15. Okay, so grab your calculator. And this one's just going to be a straight type in. We have 9,000. 1 plus 0.07. And then the exponent is 15. So in 15 years, this painting is going to be worth $24,831.28. Woo, doggy. I need to invest in a painting. I wonder how much my tigers will be worth in that many years. Alrighty. Okay. I guess too, it does say write an exponential growth function to model it and then find it. So perhaps the model, I should have put general with a T here. There you go. And then plug 15 in. All right, so there's the general model. And then here's how you find the value after 15 years. Okay, so let's look at the next question. Population of a town is decreasing. Interesting. So this time we're going to decay. All right. Let me go back a little bit here. Exponential growth. Those are those graphs that start off slow and flat, and then out of nowhere, it's like, boom, skyrockets, right? Kind of like the coronavirus is doing now. It's kind of scary, isn't it? But it exponentially explodes. Whereas exponential decay is the reverse. It decreases really fast and then it flattens out. All right. Anywho, the equation for exponential decay looks very similar to growth. It starts off with the A, and then you have the 1 here, but instead of plus, we're gonna minus, right? We're gonna minus. Why are we minusing? Because it's decaying, right? It's going down, it's decreasing. All right, so we still have the initial value, you still have the rate, we still have the time. So it's essentially the same, except instead of plus for growth, it's minus for decay. All right, here we go. There were in the year 2000, there were 1,700 people. That is a very small town. So our initial value is 1,700 people. We are decreasing at a rate of 3% per year. So 1 minus 0.03 per year. All right, we want the population in 2012. Be careful, you're not putting 2012 into this, you're putting in how many years, right? It's per year. So from 2000 to the year 2012, how many years is that? That's 2 years. So our equation looks like this with 2, right? 2 years have passed. And I'll put a little reminder, that's how we got the 2. Okay, grab your calculator and let's see how many people are left in this small town. I wonder where everybody's going. Let's see, to the 2. So 2 years later, there is 1,599. So 1,599.53 people. And it's okay that there's a decimal. This is just theoretical. You could round up and say 1,600 people. All right, okay. And last but not least, we have compound interest. This one is the most real world out there, right? This compound interest model is what calculates your credit card loan, your home loan, car loan, student loans for college, or investments, all right? It could be flip-flopped. So maybe you invest in something that has a return, like a certificate of deposit, a CD, savings account, cell phone. Anywho, the compound interest function model looks like this. This one's a little bit more complex, but you can always look it up. It's not something you have to have memorized. So you've got A equals P, A for amount, by the way, P times 1 plus R over N to the NT. Okay. So the P here stands for principal. And in the finance world, that's your initial value, right? So your initial investment, initial value. R still stands for rate. So that's going to be your percentage rate. And N is the number of times that you compound something. Have you ever heard a semi-annual sale? What does that mean? Semi-annual, right? That's half the year. You could see monthly, right? Compounded monthly. So if it's compounded monthly, N is 12. If it's compounded annually, then it happens once. If it's compounded quarterly, then that's 4. So here's little tips on it. So monthly, annually, quarterly. And of course, there's others, but those are the most common that I see. So that's what N is. So N happens twice, right? And then T stands for time. All right, so let's try one. We're gonna find the balance if we invest $15,000. Nice. So we're investing $15,000. So we have $15,000 for our initial value. All right, we're gonna invest it at a rate of 4.8%. So we have 1 plus, we're gonna drop that percent and move that decimal over 2 places, right? So 2 places, that makes that 0.048. Next up is the N. So how many times are you gonna do this? We're gonna compound this monthly. So if we're compounding monthly, then that means N is 12. All right, so we're doing this rate every month. And then for how long? We're gonna do this for 2 years. So our exponent is the 12, because we're compounding it monthly for 2 years. All right, so that's 24 months that we're gonna be doing this equation, this investment. All right, so let's see how much money we got. We have 15,000 times 1 plus 0.048 over 12 And then the power, you can go ahead and type it in as 24, or you could type it in 12 times 2. Whatever you prefer. Okay. So it looks like after 2 years, you have made now a total of $16,508.22. So you've made what, like 1,500? Better than nothing. Money just sitting there. That's good. That's good. So the amount that we have after these 2 years, $16,508.22. Not bad. All right. So the next page is some practice problems. The first set right here is your growth function. So that's going to be the a times 1 plus r to the time. The next section is that complex compound interest formula where we had the amount equals your principal investment, 1 plus r over how many times you compound it to the nt. All right. And then the last 3 are going to be exponential decay. So this section is going to be a1 minus r to the t. Check out the answer key on the blog if you're stuck on any of these. And you could always hit me up on a live Zoom chat or email me at any time. I am here for you. Yeehaw!